Extrusion is a Greek word which means push out. That means you are actually pushing the material out of the machine to get it into a shape that you desire or you design. So it pumps or supplies continuous stream of material from the system where it gets into a molten state, and then to a system where you cool it and then form it into a shape. Again, we'll see that in few minutes, but that's kind of the principal philosophy. I mean, it's pretty simple. You melt the plastic and then you push it out of a particular component, which we call it as a die, and then you cool it as it comes out of it, out of the geometry that you envision to develop. So it is used for a variety of different materials. Plastics comes to the mind most importantly, but it's also used for metals. I mean, a lot of metal extrusions that you see are, for example, even the rail tracks, they are actually extruded, metal extruded, and so many other things, like even the caulking that you do, you actually push or you press it and then the material comes out of it. That's again another the same philosophy, the same principle, and a lot of other aspects of it, the toothpaste, the spaghetti, and all these things. But in this particular module, what you're going to learn is about plastics extrusion. We're not going to go into any of the metal extrusion technology here or process physics here. We're going to purely focus on plastics extrusion. So now you're going to see a video which actually shows you the different components of the extrusion, as well as how the material gets into the molten state, how it's actually mixed, and then how it comes out of the die orifice to get into a shape, and then how do we cool it to further take the product out of it. As you have seen in the video, the principle is very simple. Continuously shaping a fluid polymer or a molten polymer through an orifice, called what we call it as a die, and then solidifying that into a product. And the solidification process can be done using multiple different ways. What you have seen in the video is more a water bath system. Again, that's basically a strand, a polymeric strand that's cooled to make it into pellets, which is what I was talking about previously, from powder to the pellet form. But this product can be, we can actually use the multiple different dyes to make multiple different products, and we'll see some examples of that today. Coming to the equipment that we use, primarily this extrusion process is of two types, a single screw extrusion as well as a twin screw extrusion, and we'll talk about both the process physics momentarily. But in general, if you take the extruder as such, it has one screw or two screws depending upon which process you select, and it has a barrel and a feed hopper and a die. These are the prime components of it, and then we'll dissect into each of these in few minutes. And then it does have electric heaters that heat the material to get it into molten state. But that's not all that melts the material. There's something else that's going on, and I'll talk about that as well. And then typically we rate these extruders with the diameter of the screw, and we also rate this what we call L by D, or aspect ratio. And typical L by Ds range anywhere between 20 to 30. That means the ratio of the length to the diameter. So we have a typical diameter which may be 22 millimeters, 24 millimeters, 26 millimeters of the screw. And then again, these are all lab scale I'm talking about. If you go for industrial scale, they are much larger, 48, 96. I mean, they're pretty huge because the throughput has to be much bigger for industrial scale. And then if that is the diameter, and the length can be in feet. So the aspect ratios are pretty large. And of course, higher the aspect ratios, you'll have more heating zones. But we can categorize all those heating zones into three main zones, which is feed, transition, as well as metering. And we'll talk about the reasoning of naming these things and what's the function of each and every zone, and how it's going to impact the overall process physics. Some additional components within extrusion system, which some of which you may see, some of which you may not see. For example, the drive system. You may not see all of these components individually when you actually go to an extruder, as you have seen even in the video. The motor, the gearbox, the bull gear, and the thrust bearing, all these things are embedded within the drive system. But the feed system is something you see when you walk through towards an extrusion system. The feed hopper, that's what you have seen in the video as well, and the feed throat, basically that's something where the material gets fed into, and we'll talk about how the material gets into the molten state. And then the screw feed section. And then the screw barrel and the heater systems is something you can visibly see on the machine. And the head and die assembly, that's also as you've seen in the video itself. The control system is basically the heart of the machine, using which you control the temperatures, the pressures, and everything that's out there. The extruder feeders are of primarily two types, volumetric as well as gravimetric. The one which you have seen in the video is a gravimetric feeder. But what's the prime difference between these two? A volumetric feeder feeds the material based on volume basis. So it doesn't care about the density of the material. So you may have two different materials with the different densities, and the densities could be varying by significant amount. I'm just giving an example here. Maybe one has 1 grams per cc, the other one has 2 grams per cc. But it doesn't matter what the density is. All that it weighs and controls is the volume, and it just feeds the material from the hopper to the feed section on a volumetric basis, on a volume basis. On the other hand, the gravimetric feeders do feed the material from the hopper to the barrel on weight basis. So which means that if you have different materials, it exactly weighs the material based on the density and accordingly feeds that into the barrel. So there's no surprise or no of which one is more better, right? Because the answer is very evident. The gravimetric feeders are more accurate and most preferred in an industrial setting. The prime reason being is it measures the weight and then accordingly feeds. So if this is especially useful when you're making short fiber composites or compounding in using a twin screw system, because the materials that you want to blend or compound or make composites out of, they may have different densities. But if you would like to have a specific proportion, like 30% of one material, 70% of another material based on the weight basis, then that's exactly how the gravimetric feeder will actually measure and then make the assessment and then provides the material into the barrel. But on the other hand, volumetric doesn't care about any of the density, so it may not give you the exact 30-40% weight ratios that you're looking for in the eventual product. As I said, the extruders are of two types. The most common one is the single screw extruder, but the twin screw is also pretty widely used. In a single screw, a screw rotates in a cylinder and creates a pumping action. And as I said, a single screw is primarily used for a lot of different, it is used for a lot of different applications, but it's primarily used for making pellets, especially coming out of a chemical plant. As I said, you get it into, you get a powder form, and then you have to transform that into a pellet form. So taking from the powder into a pellet form, and that pellet form is subsequently used, whether it's in injection molding or even thermoforming or blow molding, whatever other eventual plastics processing technologies are, you use these pellets, especially because of their ability to flow freely. So single screw is primarily used for those, and there are so many other applications as well, but that's one of the most dominant applications, and it's very widely used, most commonly used. On the other hand, in a twin screw extrusion system, you can, as the picture depicts, you can see two screws in there. And the prime reason for that is because twin screws are used for compounding. So you have these two screws that enable good mixing of the materials, which you can use it both for blending or compounding, as well as making of the composites. And then the twin screw can be of two types, co-rotating as well as counter-rotating. Co-rotating is most popular for compounding purposes, and then counter-rotating is used, but it also creates very high shear. So it's used for temperature. It's not used for temperature sensitive materials because it escalates the temperature very fast. So if you have a high molecular weight system, which is difficult to compound, again, or that can withstand high shear capability or even high temperatures, that's where counter rotating is used. The extrusion system, as I talked about, the whole barrel, the one which you're seeing in the picture, that's called the barrel, and that's the heart of the machine. As you have seen in the video, the material gets fed into the barrel, and then it goes through multiple transitions within the barrel, and then finally it comes out of the die to get it into a shape, and then you eventually cool it down to get the product. So this barrel, which is the prime heart of the machine, it's divided into three different zones, and the barrel is what we're talking about, the L by D previously, the length over the diameter. The barrel consists of the screw or screws, and the diameter of the screw, which is basically we will talk about the anatomy later on, but which is measured in 28, 30, or in industrial scale 48, 96 up to 150 or even more, right? Millimeters of the diameter, and then you have a significant length. So the L over D is basically the aspect ratio that we are talking about. So depending upon the aspect ratio, the larger aspect ratio, you may have more heating zones. So you may have multiple heating zones in this. However, we can separate out this entire system into three main principal zones: the feed section or the feed zone, and the transition section or the transition zone, and the metering section or the metering zone. So in the feed zone, you have a preheat polymer which is directly falling from the hopper, and then that goes into the feed section, and you preheat this polymer, and then you convert that into subsequent zones, which is basically the transition zone. The screw depth in this particular zone is very much constant. You don't have a lot of variation of the screw. The reason for that is basically you don't want to provide any kind of additional shear heating here. You don't see, the prime objective of a feed zone is not to melt the material too much, because if you melt the material too much, then what you're causing issues, what we call bridging. What happens is, when the material from the hopper is flowing into the screw, and if you melt the material over there, the material gets stuck there, and then that's what we call it as bridging, and there is no flow of material, and at the hopper you will see a lot of bridging of the material, and you don't want to create that. To eliminate such a situation, you tend not to melt the material in the feed zone. That's why you have a screw depth which is very constant. And this entire barrel actually is, as I said, it's set into multiple heat zones, and you actually set up a temperature profile over there, and the end melting temperature, as we talked about in the materials module, the thermoplastic materials are classified into two: amorphous as well as semi-crystalline. The semi-crystalline materials do have melting temperature, but the amorphous materials do have processing temperature. So let's take for an example case, 200 degrees centigrade is a melting temperature or a processing temperature, it doesn't matter which one. You don't want to set your feed section at 200 degrees centigrade, because if you set it, then you will melt the temperature, or your material will go into a softening phase where it completely starts flowing, and then there will be a lot of bridging over there. So instead, you want to set this temperature at 160 or 170 degrees. That way you ensure that your material doesn't get into the molten state. And by the way, the heating doesn't always come with the temperature that you set at externally. It also comes to the shear heating from the internally, which we'll talk a little bit more even in few minutes. But the shear heating comes through reduced cross section of the screw. But in the feed zone, you are keeping the screw depth constant, so the shear heating is at a very minimal. So whatever temperature the material experiences is primarily due to the external heating, that you are anyway setting it at a very low value. So you are completely ensuring that the material does not melt in the feed zone. So the length of feed zone is typically 5 to 6 turns, but it may go from up to 8 to 10 for 4 feeding materials, or 10 to 12 when materials require heat to absorb before it can be melted. Compression zone or transition zone, and this is the most important zone in the entire extrusion barrel system, primarily because this is a place where you want to ensure the material completely melts. So in the previous zone, you don't want the material to melt, but in this particular zone, you want the material to completely melt. So the materials, which is basically what we call as solids from the previous zones, gets conveyed to the transition zone, and here you're trying to melt the material. So the channel depth is decreasing, as if you can observe it in the picture. And there is a reason for that, a strategic reason for that, because by decreasing the channel depth, you are increasing the shear rate and you are inducing shear induced heat. So that heat, in addition to the external heat that you're providing through the heat bands around the barrel, are melting the material. So this particular zone, you are actually escalating even the external heating elements. So in the feed section, as I said, if the melting or processing temperature is 200, in the feed section, you're subjecting them to 160, 170. So let's say 170. Here, you're setting it up almost to 185 or so. So still 15 degrees apart from the actual melting system, but then the shear heating is so high, or you can sometimes even set this up to 190, but the shear heating is so high that it almost escalates. You want to be careful because you cannot measure the shear heating, right? So that what you measure on the control system is the temperature that you actually subject to on the heating bands. So the shear heating further escalates. And if you have a temperature sensitive material, then think about it. The externally applied temperature plus the shear heating will escalate the temperature by a big ramp. So you want to be careful not to basically set it too high. So if you set it at 185, even if it goes to up to 10 degrees more, then it becomes 195. So you're still pretty much good, or even if it goes to 200, that is still a better way. But the prime objective in this whole thing is to ensure the melt is uniform and it goes into the molten state and then it goes into the metering zone. In the metering zone, again, you have a constant screw depth because you don't want to provide any additional shear heating, but you just wanted to pump the material from the molten material out towards the die and from the die to make the product and then subsequently for cooling. That's the whole intent. And in this metering zone, you want to maintain whatever molten material that comes from the transition zone. So you want it to basically set up the external to the melting temperature range, which is basically 200, in the example that we're considering. So you wanted to maintain because the material has already experienced the melt profile in the transition zone, and you wanted to basically maintain that and then pump the material out towards the die and then make it into product and then subsequently cool it. Coming to the die zone, the die zone is where the molten material that is coming out of the metering zone is pushed or pumped out of the system to make it into product ship and then subsequently cooled to get the product out. The two prime components of this, the first and foremost one is the breaker plate, and then the next one is the screen pack. And the screen pack is primarily made out of perforated steel plate. It sieves out extraneous material, for example, any kind of ungelled polymer or dirt or any kind of foreign bodies. It also helps to remove turning memory from the melt. And then it also allows head pressure to be developed by providing resistance for pumping action of the metering zone. That way you have a high pressure zone, and then outside you have a low pressure. So obviously there is a transition of the material from the high pressure to the low pressure. But there is also a problem if at all, if when you are actually making composite, the screen pack can also increase the pressure to such a high extent because of the clogging with the composites, with the fibers, that it may actually stop the overall action of the system. So you have to be careful when you are when you're processing composites or even some high viscous materials. That's when you have to we have to take extra care in terms of the screen pack design, or you may have to sometimes even remove the screen pack to make sure the material flows through smoothly out of the die and then subsequently into the product phase. Now let's look at solid conveying. So basically we talked about in the transition zone where the material gets into the molten state. From the feed zone, the solids are being conveyed and then gets into the transition zone, and here the material starts to melt, right? Now, solids conveying is all about conveying the solids from the feed zone towards the transition zone, and within the transition zone, how the material molten phase occurs. We can explain this using plasticizing Tadmor model, what we call. As you can see in the picture, when there is a rotary action around the system, and you can see those are the two flight channels, and between which you have the material. There are solid beds which just came out of the feed zone, and then they keep on rotating, and they form a thin layer of molten film. This is due to the external temperatures that you have set, let's say 180 or 185, and that thin layer gets into the solid bed again, and then the rotation continues to happen. When more and more material from the solid bed gets melted, it goes towards the melt pool, and that's how the melt pool develops, and subsequently you have a complete molten material which is then pumped into the metering zone. And this is nicely explained by the plasticizing Tadmor model, and this is a phenomena that actually happens within the barrel of the extruder between the two channel depths that you can see over here. Some of the preferred conditions for a high dissipative melt capacity of a screw at a given screw speed could be high barrel temperature or smaller channel widths. That also could help in expediting this whole system, and very tight flight clearances, because all of these will increase the shear heating that eventually will help to melt the solid beds more profoundly and much faster, so that the melt pool can be generated at a faster rate. The mixing within the extrusion system, whether it's a single screw, you can even set up some mixing elements within a single screw system, or even in a compounding system. We can actually classify them as two prime categories: dispersive mixing as well as distributive mixing. Dispersive mixing, as the name resonates, it's a breakup of minor component of a mixture into smaller size particles or droplets. And as you can see, schematically it is showing in the picture, you can see a clustered agglomerate group of particles. Now they get dispersed into smaller particle sizes. That's basically that kind of mixing phenomena is known as dispersive mixing. In terms of distributive mixing, you can have the same clustered agglomerate particles, and then you can have a lot of them in small bunches, or you can also have a dispersive mixing done, and then those get distributed. And there are some kind of mixing elements that also facilitate distributive mixing as well. Ideally, what you want is both a dispersive mixing as well as a distributive mixing. So if you look at the four quadrants that are shown, the last quadrant is basically what we are talking about on the right hand side, which is basically a dispersive mixing as well as the distributive mixing. Ideally, that is the type of mixing you want. So your screw design that you enable should be a combination of these two, so that you can realize the eventual dispersive plus distributive mixing in your final material, and that will help you to get the best property material system, which eventually makes it into a product. And the same phenomena can be explained in shearing and elongational flow, because these are the two types of flow that the material gets experienced as it goes through the extrusion system. In the shear flow, as you can see, as the material rotates, you have a group of particles that gets dispersed within the system, and same is the case that happens within an elongational flow as well. Another important parameter that you should keep in mind is the compression ratio. So the compression ratio is defined as feed depth over the metering depth. So what is a feed depth? If you remember the anatomy of the screw, what we talked about is the screw diameter doesn't change in the feed section. It narrows down in the compression zone or in the transition zone, and then again it remains constant in the metering zone. So the diameter in the feed section to the diameter in the metering section is basically what we are talking about as the compression ratio. And this is a very important factor that determines how fast and how the heat transfer is being propagated to the material, and how fast the material gets into the molten phase, and how fast your throughput is, and how it actually impacts the properties of your materials. So that's why for every material, well-known material system, whether it's a polystyrene or polyolefins or polyesters, any kind of the thermoplastics, there are some predefined compression ratios that are set. The next important aspect you have to consider is die forming. Basically, the product gets, again, the heart, as I said, is the barrel. But if you look at the eventual thing which a user cares about is the product. And the product gets its shape in the die. So the die is the most important aspect when it comes to the product quality, and something that the customer cares about. It has its main function is to supply of the extruder is to supply homogeneous polymer melt to the die at a required rate and die head pressure. So these are the two considerations. So the extruder supplies the polymer melt at a certain rate, which is the throughput, which we call, and at a certain die head pressure, so that the pressure propagates and pushes the material out towards the towards a cooling system or a subsequent accessory system that cools the product. There are two other aspects that you have to consider: the melt quality and stability. Melt quality is defined as the quality of the melt that's flown into the extruder through the die and gets into the product, and also the stability. And the stability actually is more important because it will ensure there is a consistent yield and product that's coming out of the extrusion system. And when you talk about the melt quality, there's another terminology that you have to clearly distinguish, which is the melt quantity. The melt quantity is the output rate or the throughput rate, how much amount of material is coming out. And extruders are actually rated by this. There could be some extruders which have 4 pounds per hour, or 20 pounds per hour, 4 kilograms, 400 pounds, 200 pounds. So the throughput changes very drastically depending upon whether you're using a lab scale extruder versus an industrial scale. Of course, in an industrial scale extruder, obviously the throughputs have to be much higher, basically to meet the production demands. When it comes to the melt quality, the closeness of the melt temperature to the desired level. Again, we talked about feed zone, transition zone, and metering zone. And then in the metering zone, we set it everything to 200. And in all idealistic cases, there are absolutely no heat losses, is something what we assume. Everything goes too smoothly. But what if there are heat losses? Then we desire to put the temperature at a constant rate of 200, but there might be a lot of fluctuations within that. Due to heat losses, it may go down, or due to additional shear heating, it may go up. But if you can keep the melt temperature as close to the desired level, so if you wanted the desired level to be 200, you can set it to probably if you get it for 205, 202, 203, 204, 198, 197, like that, and that means the quality is going to be pretty good. And then the melt temperature distribution across melt system measured at a given time should also be consistent. That means when a material is coming out like this, let us, if this is a material that is coming out, and the distribution of the temperature profile in this whole thing should be very uniform. Otherwise, you could see some burning domains or regions that may eventually impact the quality of the product. and the degree of and uniformity of mixing across melt stream. Again, if within the barrel, if you don't measure a consistent and more uniform melt profile, then what happens is the mixing will not be so much uniform, and then eventually your product that comes out may not be as homogeneous. You aspire every bit of it to have 40% of material A and 60% of material B, but it may fluctuate anywhere between 30 to 70. And that will change your product properties too, because you have designed a part based on certain properties, and those properties are designed based on 40-60 ratio of two material mixture. But if your melt mixing is not uniform within the barrel, then you may end up with 30-70. That may change the material properties, that may eventually even impact your entire product design. The next thing is residence time distribution. Residence time is a very interesting factor. The reason being is, if you actually keep the material within the barrel for a longer time, this is especially more challenging when you have a long L by D or high aspect ratio extruders, because the material stays inside the extruder for a long time, right? Now, with such a long duration, if the material is temperature sensitive, then you may actually see degradation of the polymer. So of course, the other side, how can you overcome? You can actually pump out the material way too fast. That means you're rotating the extrusion at a very high speed. What's the disadvantage of that? By rotating the screw at a very high speed, you're actually having a lot of shear heating that may also escalate the overall temperature of the melt system, which may also disrupt the overall quality of the melt. So you have to be careful of the selection of the extruder for your material system. You don't use the same extrusion system for a host of different materials. That's why when you first go and try to buy an extrusion system, the first question that the salesperson asks is, what materials are you trying to extrude? Depending upon that, he will give you some normal specifications of the L by D, which is the aspect ratio, the screw diameter, the screw design, and all those things. When it comes to the melt stability, the melt temperature fluctuation with time, which is measured at a given location, that's actually very important factor. And very similar to that, the variation in the degree of mixing, that will also impact the stability, as we talked about within the quality. And the melt pressure fluctuations. And why does this happen? The melt pressures gets fluctuated due to multiple reasons. If there are some contaminants, that may actually change the viscosity, and that may actually even create some slippage within the material system that may actually vary the pressure of the melt as such. So these are all the different things that may impact the overall melt quality, quantity because of the throughput, as well as the melt stability. If you can control all of these things, then your eventual product performance will be much better. Residence time or dwell time, as we talked about, that will significantly impact, especially if you have temperature sensitive materials. So care should be taken at most in terms of dealing with such kind of materials. And one simple example is bio-based plastics, polylactic acid. If you are actually dealing with this kind of material system, they have very narrow processing ranges. That means that you can process them between 185 to 195. Let us say, I'm just for polylactic acid, it's actually true, 180 to 190, right? In fact, 160 is basically, or 167 is its melting temperature. So up to 180 is fine. So anywhere between 160 to 180 is basically what you're looking for. And that's a very narrow processing range, because if you have an extruder which has, let us say, 30 L by D, that means it is pretty long. Then you have to set up everything at 5 to 7 degrees increments, which is tough to maintain, number one. And number two, the shear heating goes up pretty fast or pretty high, that it's very difficult to maintain within such small temperature range. On the other side, if you take polypropylene, it can be processed anywhere from 165 degrees to all the way to 220 without any degradation. And that's basically the processing window we're looking for, which is most important. So a lot of work is being done to extend the processing window, and there are so many other things which I'll talk about eventually later.